Okay. So today we're discussing the weak law of large numbers, and I mean, as I said before, I'm not even 100% sure that we're supposed to cover this in this class as opposed to 661. I think it's supposed to be in this class, but well, the way that I'm teaching this class, and nobody really told me what I'm actually supposed to teach. But it's probably going to be, it's something you should definitely be familiar with because these various laws of large numbers and the central limit theorem are probably the most key results in all statistics. And almost all statistical inference that you do in a day-to-day life depends on these results. Now that said, it's really hard to write problems involving these theorems, so they don't tend to show up much on qualifying exams. So I'm presenting this because I think you need to know this stuff just in terms of statistical literacy, but less so because I think you're going to fail your quals if you don't. So most likely in terms of homework and exams, it will be evaluated very loosely, if at all. And that, I'll be honest, that a lot of that is my laziness as well, because when they did this before, I didn't really have problems on this, and I'm not sure I want to take the time to write any, so it's FYI. So, and the math here is a little bit hairier than you'll see in most of the rest of the class as well. If you're going to take 760 someday, try to study this well enough that you follow it, because you'll be doing all this and significantly hairier stuff, improving some of these results in even more generality. If you're just taking the MS courses and some of this goes over your head, don't worry about it. In all probability, you're never going to be evaluated on this. Just as long as you understand the main results, that's really all that you need for the MS level. Any rate, so weak law of large numbers. The idea is, say we have a bunch of random variables and we take the average of them. We want to know about the limiting behavior of this average as the sample size gets large. And as I said here, first I'm going to look at this under some fairly restrictive conditions, then I'll work on relaxing these conditions and show that these results still hold after the conditions are relaxed. And throughout this lecture today, to illustrate that y bar depends on the sample size that you're averaging over, we'll denote it by y bar sub n, which basically just means the average of n things. So first we're going to discuss the convergence and probability of y bar the n. That's all we're going to discuss today. This is the weak law of large numbers. Basically what we're going to show is that if you take a sample of a bunch of things that have some mean and then you average these various samples together, it will converge to the mean. Today we're discussing the weak law of large numbers, which is this idea that it will converge to the mean in probability. On Thursday, I think we'll be discussing the strong law of large numbers, which says that the sample mean converges to the population mean, not just in probability, but also almost surely. If you'll recall, I guess it was about 2 weeks ago before the midterm, we discussed convergence in probability versus convergence almost surely. If you understand the difference between the two at this stage in your career, you deserve a donut. But we'll be proving both results. If you take 760, hopefully it'll make more sense then once you've had more time to digest in your brain. If you're not going to take 760, it's probably never going to matter anyway. And one quick note that when we talk about these law of large numbers, we're talking in the long run, that just because you flip a coin and get like 5 heads in a row doesn't mean that you're now going to get the tails are overdue and you're going to expect a greater number of tails. In the next 5 tosses, the tosses are still independent of one another. That the idea is once the sample size becomes extremely large, you're going to get closer and closer to the true mean, but just because in a finite sample you're a ways away from the true mean doesn't mean there's going to be a correction in the next little while. So, the first weak law of large numbers, which is the weakest weak law of large numbers, basically the weak law of large numbers with the most restrictive conditions, that we're going to assume the various yi's are IID, that is independent, identically distributed, with the same mean and variance. Over the course of the rest of today's lecture, we're going to relax these conditions one by one. That will show that this result still holds even if they're not identically distributed, but they just have the same mean bounded variance. We're going to show that you can sometimes get this result even if the variance is infinite. We'll also show that you can relax the independence assumption to some degree. But for the time being, simplest case where everything's independent and identically distributed. And we're going to assume that, well, not assume, actually you can prove that the expected value of the sample mean is mu and the variance is sigma squared over n.
This is like more based on like the previous question in general. For weak and strong law of large numbers, it doesn't change like what assumptions, like you're saying, like you relax the assumptions. The only difference between weak and strong is whether it converges in probability or.
Yeah. That.
They have the same underlying.
That's a good question, actually. I do not remember for sure off the top of my head to what degree the results we're discussing today are still true for the strong law. I mean, same thing I was saying before about half the stuff in this class I don't really remember until I prepare my lecture the night before, if I'm being honest. That my recollection is that there is a form of the strong law where all you need is finite means, and it holds with finite means and infinite variances. To what degree you can relax the independence assumption, I honestly do not remember. Come back Thursday and hopefully I can tell you. But at any rate, fairly easy to show. Expected value of the sample mean is mu. The variance of the sample mean is sigma squared over n. So, given that result, we can just use Chebyshev's inequality. We discussed this briefly before the last lecture, but by Chebyshev's inequality, the probability that x minus mu is greater than or equal to t is less than or equal to the variance of x over t squared for any t larger than 0. So we'll replace x by yn bar, and that gives us that the probability that y bar sub n minus mu is greater than or equal to t for some t's less than or equal to sigma squared over nt squared, which gives us that the limit as n goes to infinity of this probability is 0, which is the very definition of convergence and probability to mu. So we proved the weakest weak law of large numbers, woohoo. Now, let's start by relaxing these assumptions, as I said. Let's not assume that these numbers even have the same distribution at this point. Let's just say that they're independent of one another, well, not even necessarily independent, it suffices to say uncorrelated, and they all have the same mean. They don't necessarily have the same variances. All we know about the variances is that they're uniformly bounded. That is, you can find some m such that all the variances are less than or equal to n. Given those conditions, the weak law of large numbers still holds. And the same proof basically works, that by Chebyshev's, the probability that y bar sub n minus mu is greater than or equal to t is less than or equal to the variance of y bar sub n divided by t squared. And this time the variance doesn't have a simple form, but the variance is uniformly bounded by this upper bound m. So that tells us that the variance of y bar sub n is going to be 1 over n squared times the sum of these sigma j squareds, which each one of them is less than or equal to m. so their sum is less than or equal to n times n divided by n squared is m divided by n. So that gives us the variance is bounded by m divided by n. So that tells us the probability that y bar sub n minus mu is greater than or equal to t, less than or equal to m times m divided by n times t squared. Again, that's going to 0 for large n, so that gives us that y bar sub n is converging to mu in probability. Therefore, given any set of uncorrelated random variables with common mean and bounded variances, we still get the weak law of large number. Okay, so next thing that we're going to try to relax is the uncorrelated requirement. Let's say that rather than assuming that the variables are uncorrelated, let's assume that they're bounded by some value m. Well, turns out that doesn't work because if the variance of y bar sub n in this case be 1 over n squared times the sum of the various covariances, there's a total of n squared of these covariances. So that would give us that the variance is bounded above by m, but note that there's no n here. We're hoping to bound it above by something that's divided by n, and as an n in the denominator, so that as n gets large, it goes to 0. There's no n there. This is not going to get smaller for large n, so it doesn't work. And in general, if all your variables are correlated, the weak law of large numbers will not hold. So we need a stronger condition than that. The general trick is if you want to relax the independent slash uncorrelated requirement, then you need to make sure that some of the yj's and yk's are uncorrelated. There's various ways to do this. I think if you take 760, you'll get to explore all the conditions under which this works. But for the time being, we're just going to give one simple example that the that the argument based on Chebyshev's inequality will still work as long as you have what's sometimes called ergodic dependence, or the more informal idea is clumpy dependence, that things that are close together are correlated, but as you get further and further apart, they become closer and closer to being independent. Like if you have time-ordered data, this assumption often holds that if you measure something, if, say, for example, you're measuring, I was working on a project a while ago with a collaborator in the biology department, measuring like the location of a moth's wings as it flew. And like if you look at the location of the moth's wings at 0.7 seconds and 0.8 seconds, they're going to be really strongly correlated with one another. But if you look at like 0.7 seconds and 37 seconds, well, then the correlation is likely to be quite weak. And as long as you have this general ergodic dependence, meaning that the further apart two observations are, the closer they are to being independent, then the weak law of large numbers still holds.
How would you prove something like that? Like, how can you actually say that, the farther along you get? Like, maybe you can get super far, but there's some, like, lower bound that you don't get below in terms of
Prove? I mean, I've, like, corrupted you in this class where we actually prove stuff in the real world, like, psst. I mean, in general, and it's kind of one of my frustrations with statistics in the first place, that to publish in the top tier journals, you're supposed to have lots of math in your paper and prove that your method works. Well, how do you prove that your method works? Well, you say that if this condition, this condition, this condition are satisfied in the data, then we prove that the method works. How do you know those conditions are satisfied? You don't. I mean... Yeah, I mean, you can tell my personal biases on this thing, but to me, I prefer a method that just actually gives good answers. rather than a method, there's some elaborate mathematical theory that it gives the correct answers when you can't test the assumptions of the theory in the first place. Now, having said all that, with this sort of thing, I mean, the simplest thing to do, assuming you have your data, I mean, in principle, it's easy enough to just look at the correlation between observations at t and t plus 1, and then t and t plus 2, and t plus 3, etc. If you have a long enough time series, you can do this for fairly large gaps, and you would hope that the correlation between larger gaps is getting smaller and smaller as the gap size increases.
Does that imply it goes to 0? Like, could it go to like 0.001?
Yeah, it could, and you can't rule out that possibility. That, I mean, if you have enough data, I mean, you could do a formal test of the null hypothesis, the correlation is non-zero. And if you have a very large sample size with really dense data, that if you have like a huge time series with hundreds of thousands of observations, and when you do lags of size 100, your correlation is 0.0003 with a p-value of 0.9997 for the null hypothesis of no correlation, probably say, okay, fine. Once you get far enough apart, they're close enough to being uncorrelated. But, I mean, it's the sort of thing that, in general, when you do any type of mathematical or statistical model, you just have to make some assumptions that the data satisfies some properties that you think are reasonable. But in general, testing those properties are very difficult to do. I mean, you just start at a very basic level. That Percy Diaconis, famous probability theorist, who was one of my professors at Stanford, has really fascinating life. That ran away from home when he was a teenager to join the circus where he did magic tricks, and became fascinated by like the probability theory behind card tricks, and eventually went to Harvard and became one of the world's leading probability theorists. But at any rate, he used to give this demonstration in class just to illustrate the idea that sometimes assumptions that we make about even basic things aren't necessarily satisfied. You just pull out a coin and just be like, so we all know the probability of heads is 1/2, and they're all independent of one another, and over the long run, you'll get approximately 50% heads and 50% tails, and then it'd proceed to flip the coin so that it would land heads 10 or 15 times in a row. How do we know that can't happen? We don't. And in fact, I think Percy and his wife actually wrote a paper once showing that in general, coin tosses are biased, that the long run probability is slightly greater for heads than for tails, and there's a really strong bias for the coin to land on whatever side is up when you flip the coin. So we use this fair coin example countless times in probability and statistics. In actuality, even this most simple example, all our assumptions for the problem are wrong. So hopefully I haven't destroyed all your faith in modern science, but this is general principle to be cautious about this sort of thing. And I guess I can ramble about this because today's lecture is short. So anyway, any other questions about this? It's not going to be on the exam, but I do think it's important in terms of statistical literacy. Okay. So if that assumption holds, then we'll use this notation. Let's just say that the covariance of yj, yk is some value sigma of j minus k, where this value of sigma depends only on the difference j minus k, or the absolute value of j minus k. I know this notation's a little bit confusing. The idea is that, we'll just use like a time series example again, the idea is that any observations that are within one of one another have a covariance of 0.7. If they're 2 apart, they have a covariance of 0.3. If they're 3 apart, they have a covariance of 0.1, whatever. That's the basic idea. That, in general, the distance between successive observations determines the covariance. And the condition that we place on these covariances is that you sum this sigma of j over all possible values of j, and it comes out to be something finite. then that obviously implies that sigma j is going to 0 as j gets large, because if you remember from analysis class, if an infinite series converges, that implies that each term of the series must be going to 0. If that condition is satisfied, then we can write the variance of y bar sub n, which is of course the sum of all these covariances, and you can break this up into two pieces. There's n pieces in that where it's just covariance of yj comma yj, which of course is just the variance of yj for each one. So that's n times sigma 0, which is just the variance of any one term in that piece, and then plus 2 times the covariances of the cross terms, the y1, y1, covariance y1, y2, covariance y1, y3, covariance y1, y4, etc. And if, trying to decide if it's even, you can just take, if you don't see why that expression's true immediately, it will hopefully make sense if you write it all down. I can go through that if anyone's really curious, but just kind of an annoying detail that isn't that essential to the proof, and like I say, it isn't really essential that you understand all the details of this proof for this class anyway. You can just take my word for it that if you write it all out, you end up with an expression equal to that second piece. So you'll note the outside of the fraction is 1 over n squared, so we bring a 1 over n inside the parentheses. N times sigma 0 divided by n just goes to sigma 0. 2 times that summation then turns into summation of 1 minus j over n times sigma j. And now what happens is n goes to infinity here. Well, sigma 0 is obviously bounded by sigma 0, but the second piece here, 1 minus j over n is less than or equal to 1, so this whole piece is less than or equal to 2 times the sum from j equals 1 to infinity, sigma j, which by assumption converges to some number m that's less than infinity. So this whole sum is less than or equal to 1 over n times sigma 0 plus 2m. And that was what we were trying to get in the first place. We've now bounded the variance of y bar sub n by something that goes to 0 as n gets larger. So if we plug that back into Chebyshev's, we get that the probability that y bar sub n minus mu is greater than greater than or equal to some value t is less than or equal that upper bound divided by n times t, which goes to 0 as n gets large. So if this particular condition here is satisfied, that number one, that the correlation between successive terms is getting larger, and or if the correlation between successive terms is getting smaller as the terms get further and further apart and they sum up to something finite, then the weak law of large numbers still holds. And it is worth noting here that it isn't sufficient to just say that it's going to 0, that there could be some values of sigma j, like sigma j equals 1 over n is a famous example. That series does go to infinity. And if you were going to test this in real life, probably what I would want to do is hopefully once the successive terms in your time series are sufficiently spaced out, the correlation is essentially 0. And in that case, you're summing over only a finite number of things, in which case the sum is definitely finite. But like I say, it can be hard to test these things. So the proofs of the weak law of large numbers thus far require the second moment to exist. And it turns out that we can weaken this condition further, that if a distribution has finite mean but infinite variance, in general the weak law of large numbers will still hold. But we can no longer use Chebyshev's inequality in that case to prove it because Chebyshev's requires a variance. As you'll recall, I think it's the T distribution with 2 degrees of freedom. I can never remember which one it is exactly, but that's the example everybody points to of a distribution that has finite mean but infinite variance. And we'd like to know, does the weak law of large numbers hold for such a distribution? It turns out that it does, but we can't use Chebyshev's to prove it. So we have to come up with another approach that doesn't rely on Chebyshev's. It turns out that you can do this using characteristic functions and specifically the relationship between characteristic functions and convergence and probability / convergence and distribution. Recall the definition of convergence and distribution, or at least the definition we're using in this class, that xn converges in distribution to x if and only if the pointwise limit of the sequence of distribution functions converges to the distribution function of f for all continuity points of f. And if you remember from the lecture 2 weeks ago that in general, convergence and distribution does not imply convergence and probability. It does if the limiting distribution is degenerate. That if yn converges in distribution to y, where y has a degenerate distribution, that is, that the probability of y equals a is 1 for some constant a, that implies that yn also converges in probability to a. So, in other words, that to prove the weak law of large numbers, if we can show that the y-bar sub-n's are converging in distribution to mu, that implies they also converge in probability to mu, because if it converges in distribution to if the sequence of random variables converges in distribution to a degenerate random variable, you can think of it as a constant random variable. That isn't technically true, that a random variable that's equal to some constant with probability 1, then it's also converging in probability to that constant. So, this is an important theorem known as the continuity theorem that, again, very important to know if you plan to take 760 someday. Say, let's suppose the moment generating function of a sequence of random variables exists for the absolute value t less than some value h, and the moment generating function of the limiting random variable y also exists, then y sub n converges in distribution to y if and only if the pointwise moment of the moment generating functions is the moment generating function of the limiting random variable y. The idea is if you want to show that a sequence of random variables converges in distribution to something, it suffices to show that their moment generating function converges to the moment generating function of the distribution you're trying to prove that it converges to. Well, that's great, but it doesn't really help us for proving the weak law of large numbers, because as you'll recall, in order for the moment generating function to exist, all moments have to exist. In particular, the second moment has to exist, and if the second moment exists, then we could have just proved the weak law of large numbers using Chebyshev anyway. If we want to be able to prove the weak law of large numbers where the second moment doesn't exist, we need a way to do this that works even if the moment generating function doesn't exist. Well, if you remember our discussion on this, hopefully you've already thought of the solution. It's basically the same trick holds for characteristic functions, that y sub n converges in distribution to y if and only if the pointwise limit of the characteristic functions goes to the characteristic function of the limiting distribution. And the advantage of characteristic functions over moment-generating functions is that the characteristic function always exists even if no moments exist. And so finally, remember the characteristic function for a degenerate distribution is just e to the ita. That's easy to prove. The definition of the characteristic function is just the expected value of e to the itx. Well, in this case, x is equal to a with probability 1. Expected value of e to the ita is just a constant, e to the ita. So that means that if we can show the limit of the characteristic functions of y bar sub n is e to the ita, then we've shown that y bar sub n converges in probability to a. And they put the little note in the slide. They put the exclamation point because they were excited. That is not intended to suggest that yn converges in probability to a factorial. Anyway. So now we'll do the weak law of large numbers without assuming that the variance exists. That, say, you have a bunch of random variables having finite mean, that is their expected value, is less than mu, then the sample mean converges in probability to mu. This holds even if the variance is infinite, like the t-distribution with 2 degrees of freedom. So, quick outline of the proof. I won't bore you with the details because it's not essential for this class. You'll get to learn more if you're taking our PhD classes, but the basic idea is that the characteristic function of y bar sub n is just phi of t divided by n to the nth power. You get that result because, as you'll recall, if you to find the characteristic function of x1 plus x2 up to xn, that's just the characteristic function phi raised to the power n, and then in general the characteristic function of a constant times x is just the characteristic function evaluated at c times x. So in other words, the characteristic function of y bar is going to be phi of t divided by n to the nth power. So our goal is to show that the limit as n goes to infinity of phi of t over n to the nth power is e to the I mu t. That the way we show this is just do a Taylor's expansion for the characteristic function around t equals 0. Since the first moment exists, that implies that the derivative of the characteristic function evaluated at 0 is equal to I times mu. So that implies the Taylor expansion of phi of t over n to the nth power is going to be equal to 1 plus t over n times I times mu, the first derivative evaluated at 0, plus a remainder term that goes to 0 as n gets larger. If you've been listening to the 690 material for this class, then hopefully you recognize the remainder for Taylor's theorem here, as well as this little o notation, meaning something going to 0 as n gets larger. If you're not in the 690 section, then you don't need to worry about it. If you are and you don't recognize this well, this is a good opportunity to review because you'll want to know it next year. At any rate, so the little o term is going to 0 as n gets larger, and the remainder, hopefully you recognize as that in general, if you have 1 plus a divided by n to the nth power as n goes to infinity, that just converges to e to the a. Hopefully you remember that from calculus. One way or another, in this case, we have 1 plus I times t times mu divided by n to the nth power. That implies the limit as n goes to infinity is e to the I times mu times t, which is precisely the characteristic function of a degenerate distribution that's equal to mu with probability 1. I guess I didn't put the punchline at the bottom of the slide. So that gives us that the y bar sub n is converging in distribution to mu, which implies that it's also converging in probability to mu. We've just proven that the weak law of large numbers still holds even if the variance is infinite. There is no way to relax the assumption that the first moment is finite. However, it has to have an expected value. I mean, that makes intuitive sense, but the Cauchy is the standard example of a distribution whose mean is not finite, and you can actually show that if you take the mean of n Cauchy random variables, you just get another Cauchy random variable back. If you take, like, if you have 100 Cauchys, the distribution of y bar sub 100 is another Cauchy. So the implication is it does not matter how many Cauchys you average together, you're not going to end up with something that gets closer and closer to the quote-unquote mean of the Cauchy distribution. The dispersion, it will have just as much variance as the original data, whereas if you do it for the normal, for example, the distribution will get a bell curve with the higher and higher peak around 0 if the mean 0 or whatever the mean is. Cauchy, you'll end up with exactly the same distribution. It will not converge to the center of the distribution no matter how many things you average together. A couple more quick examples of how you can use the continuity theorem to show convergence and probability. That say you want to show that the Poisson distribution converges the binomial distribution. I think we've done this before, but now let's say we want to do it using characteristic functions. Well, recall that the characteristic function for a binomial distribution, or characteristic function for a binomial distribution, in this case we have a binomial distribution with n trials and probability of success sigma divided by n. Characteristic function is 1 minus sigma over n plus sigma over n times e to the it to the nth power. And actually, I guess I said this wrong. This is the moment generating function, not the characteristic function. Not that it really matters. No, that is a characteristic function. Sorry, I need to sleep more. Anyway. So we can rewrite that as 1 plus sigma divided by n times e to the it minus 1 to the nth power. Once again, we have something that's 1 plus a divided by n to the nth power. So that means that it converges to e to the lambda times e to the it minus 1, which is the characteristic function of a Poisson random variable. So we've proven that it converges in distribution to the Poisson here. Cool. Next example, say we want to show the consistency of the empirical variance. I guess I haven't taught you this idea of consistency yet. You'll learn more about this in 661, but the intuitive idea behind consistency is that if you're trying to estimate some unknown parameter, that if your estimator is consistent, what that means is that as your sample size goes to infinity, you get the correct answer. That's usually the bare minimum property that you want any estimator to have, because if you're still getting the wrong answer for large sample sizes, there's usually something fundamentally wrong with your estimate. So what we're trying to show here is that the usual estimate of the variance, that you just take the mean and then take xi minus x bar squared, add those together, divide by n, whatever the case may be, that for large n that converges to the correct variance. And I guess technically divided by n minus 1, precisely because we want it to be consistent and unbiased and so forth. But so if we define the sample variance to be 1 over n minus 1 times the sum of xn minus x bar squared, and hopefully you saw that typo as readily as I did, that should be xi inside the parentheses and not xn. I'll try to remember to fix that. And actually, we don't know this, but you may have learned in another class that that this random variable n minus 1 times Sn squared divided by sigma squared has a chi-squared distribution with n degrees of freedom. I don't think we'll get to that in this class. You may cover it in 661. Otherwise, you can just take my word for it or prove it yourself. It's actually not that hard to do. But at any rate, if you're willing to take my word for that, then the characteristic function of I think that's another typo, that should be y sub n, not x sub n, is 1 minus 2it to the n over 2, the power of n over 2. So that implies the characteristic function of Sn squared is going to be 1 minus 2it times sigma squared divided by n minus 1 to the minus n over 2. And here, if you do like some sort of substitution, u equals minus n over 2, then you end up with what's essentially 1 plus it sigma squared divided by u to the power u. That converges to e to the it sigma squared, which is the characteristic function of a degenerate distribution with the probability that y equals sigma squared equals 1. So we've shown that our empirical variance is continuous. Any questions about any of this? The math here is a little hairier than we've done in most of the rest of this class. Don't worry about the details too much, particularly if you never intend to take 760. The important thing to remember here is just the big top line results. What are the conditions under which you can average things together and have it converge to the population mean? The short answer is the first moment has to exist, and they can't be too highly correlated with one another. Okay.